Welcome to another video. In this video I'm going to discuss some of the things I've been doing lately. And one of these things is that I made a little MOSFET tester, like I said in my previous video. Basically this is a half bridge configuration. It's using a simple driver. This is the signal inputs. Here's the signal inputs. These are the MOSFET pins. Just plug them in. These are the outputs. You can test high side and low side separately. And I'll hook it up so I can demonstrate it. So you can see that it's very simple. You can just simply connect the MOSFETs to the connectors, the screw terminal connectors. And also, if I attach a positive voltage from this boost converter, you might see a couple of sparks. So it's on. First of all, what I'm going to do first is, as you can see, it's drawing a lot of amps, which is very bad because it's going in some sort of, and you see it's shorting out. So what I have to do first, as you can see, the high side MOSFET is very hot. That's due to I excluded the pull down of the gate. So I will attach a external resistor to it, and to the ground of this 5-volt regulator, and as you can see, the amperage dropped from almost half an amp to almost nothing, because this is idle current. Most of the current is coming from the LED. So why did it do what it do? It's because, one, the signal is not attached, therefore it's floating and it's not being pulled down. So first of all, I'm going to attach the signal. You can see, very easy. And then I'm going to attach the gate driver. And now I can remove as you can see, it's still an idle current. So all's working well. And why I built this is so I can test these MOSFETs for my motor drivers, because I'm going to use a whole sack of these MOSFETs, and I'm going to have to test which one works best, because I'm going to switch very high currents, and it's actually meant for motors. It has to drive motors, and one of these motors I have here. Oops, this is not a motor, this is a gearbox. The motor is right here. As you can see, this requires a lot of thick cable, and if I can show you, is that it's using very thick copper. So it's a very high current motor, and it has to drive these, two of these. So now I'm going to test with these simple DC motors, and I'll set it up quickly. So for my motors, I'm going to attach some alligator clips to the terminals. And first of all, we are going to test the high side. So basically, the source is connected to the drain of the low side, and the low side drain and high side source are connected to this terminal. Therefore, if you want to test the high side, you connect to this terminal and the ground terminal. This is ground. So if I put the terminal against this alligator clip, it should turn, which it does. And even for this small of a motor, it has a lot of torque. As you can see from the amp, it's now at 300 milliamps. Now it's at 290. So it's a 30 milliamp increase, and if we apply some counter torque, it quickly flies up to almost half an amp, and it's still turning, as you can see. Now it's in shutdown mode. I think I can increase the maximum amperage, but my DC supply that's supplying this can only deliver half an amp. So as you can see, it will crap out. And now I will test the other motor, which I haven't tested yet. This huge 300 watt motor. I haven't tested it, as I said. So this is also new for me, and if it goes wrong, you will see as well. Yes, the power supply can't deliver that much amperage. I think it's 1 amp in idle mode. But as you can see, it doesn't supply it. I will have to get a much beefier power supply. But now I will test the low side of the MOSFETs, which is simply 1 to VCC, which is the drain of the first high side MOSFET, which is connected to VCC, and this one to the drain of the low side FET. And as you can see, it's turning. This should also work. It's a lot faster now, as the duty cycle isn't limited again. This is full duty cycle. And it's a lot of torque it can apply. Let's see at the amperage. Look, it's almost shooting up to 1 amp. It's almost at an amp, 95. But this is for a simple 50% duty cycle. But as you understand that we are going to use a lot of high torque at the motors, so we are going to require all of that power. But in fact, this little MOSFET tester over here, I'm going to disconnect it. Show you some of the cool stuff. The traces, for example, as you can see here, lots of thick copper traces. This is all VCC ground, and this is the drain, the source, drain source connection. As you can see, there's a very tiny gap over here, which is the gate. It's very dangerous, but there was no other way to do it. Oh, well, I could have routed it this way, but copper traces are very hard to bend, and I will have to make a separate design for all the traces on my main board. But yeah, you can test any MOSFET you want, and it also has AND gate capability, so you can also test the signals you are pushing through. It has headers, so if you want to turn one MOSFET off, it's now off, but it's not being pulled down. Therefore, maybe not a smart idea, and I have to add a pull down resistor. And I think I even have it the wrong way. That's why it didn't work very well. But this is a test device, and the bigger device will have 4 of these boards on one board, and it's going to be a lot of work, as you can see from these traces. But that was it for this. So what is to be expected in the next 2 weeks? Well, I'm going to be building this circuit. It's a big circuit. I'm going to be building this circuit right here. I made a video about it, and yeah, I'll be building it on this little board. Actually, for something like this, you want to use a actual PCB manufacturer, because as you can see, all the traces that are on this board are insane to solder on yourself. But I have no choice. I have to do it, because these massive copper traces, they also have to be made. And I have never built my own PCB before using an actual manufacturer. But what I've also done is I've made this little encoder. What it does is it has 2 opto isolators. They are slotted, therefore when they are interrupted, when the photo interrupters are interrupted, there will be a digital signal, because this is actually a LED with a transistor, and there are 2 of them, and I will talk a bit more about this in a later video, because I'm going to do a lot of testing in a couple of weeks, and more on this later. I'll also demonstrate it and what it's used for. But yeah, most of my time is going into building this circuit on this board. Fun part is that this circuit over here is 1/4 of this circuit. So as you can see, two MOSFETs, which are these 2 MOSFETs, gate driver, also seen over here, and bootstrap resistors, gate resistors, except I've got these pull downs, as you saw in my video. And also I didn't really work with the shutdown pin of the gate driver. It's just been connected to ground, but I will use it for safety purposes. And basically this will be made 4 times and put in this board, which is going to take a lot of time because I have to do all these thick traces times 4. Maybe it's a little simpler than that, but we'll have to see. I'm going to start it next week, I think. Yeah, and that's basically where most of my time is going. Maybe I'll also talk a little bit about the new theory I have been working on with the Railgun. It's basically if you have a conductor and resistance, as you know, it changes per temperature. Therefore, what material will heat up faster and what material is more conductive at a higher temperature. Because most people would say that copper is a better conductor for rails in a railgun, but I'm not so sure about that, because the temperature coefficient for aluminium is better, for example. So that's a little bit of a research topic. And I also have kind of thought about a layout for the rails and capacitor connection, because I want the rails to be interchangeable, but also that they have maximum the current is distributed so that there are no concentrations at the certain rails. Because, for example, if I take this as the rails and you connect a positive voltage against here and the armature sliding around here, what you will get is that if the voltage is over here, it will just go directly to the armature, which will create concentrations of high current in this area, and that's not good. So I want to try and get the current from this path, so that it has to go all the way through the material, and that no high concentrations of current will exist, and hopefully have a better connection between projectile and rails. Also, hopefully it will increase the longevity of the rails. And yeah, there's not much I have to tell. Also, I've been starting for my capacitor charger. This is only the transformer I've salvaged from a ATX power supply. Lots of things you can salvage from it. For example, some pretty quality chokes and such, which I can use. So I'll be working, I have lots of things to do before I can show actual results. But for the robotics project, I kind of have to hurry. So that's where most of my time is going. Yeah, that was kind of basically it. And thanks for watching.